This video, we're going to go through practice problems for MTE, rational exponents and radicals. Rational exponents are exponents that are fractions. We're going to lead to radicals because anything to the 1 over n is the nth root of x. Anything to the m over n is the nth root of x to the m. So those are two of the rules of exponents that we're going to be focusing on in this section of problems. First problem asks us to simplify this problem by writing it in radical notation. So we're going to have the square root. We don't write an index of 2, it's assumed to be there. If we don't write it, that's a square root of 16. So is 16 a perfect square? It sure is. It's 4 squared. So the square root and the squared undo one another and leave us with an answer of 4. You're going to want to know your perfect squares, your perfect cubes for this part. Remember that you're not allowed to take the square root of a negative number and get a real answer. We're going to do some of that though, where we take the square root of -1 and we get answers that have I in them later on in the problem set. So hang on to that. We're going to deal with some imaginary or complex numbers here, but we are allowed to take the cube root or an odd root of a negative number like this. -125 to the 1/3 power is going to be the cube root of -125, which is the cube root of -5 to the 3rd power, because negative times a negative times a negative is a negative. So this answer simplifies to -5. Now we want to rewrite this expression, 9x plus 2 in parentheses is raised to the 2/5 power. We're going to write that in radical notation. So the index is 5. Inside is 9x plus 2 squared. Nothing that we can do to simplify that because we don't know what x is. If x comes out to be something though, that when I square it, it becomes some has a factor that has a perfect fifth, then we can go ahead and pull that out to simplify. It says to use the calculator to approximate the square root of 38 to 3 decimal places. So we're going to use our calculator tool. This is one of the only classes in the whole section where you need to use a calculator. So calculator here, we have, let's see, that doesn't even have, oh yes, it does. 38 square root. There we go. Some calculators, you put the square root sign in beforehand. If you have a scientific calculator, if you have a basic calculator like this, then you are going to have to put in the square root afterwards. So this is approximately 6, and it says to 3 decimal places, 164,000. So it wants us to round to the nearest thousandth there. Now we're going to approximate a square root though without the use of a calculator, and I like this because it makes you have to know your perfect squares. So we're going to say that the square root of 73 is going to be somewhere between what two integers? Well, it's going to be between the square root of 64 and the square root of 81. Those are my closest perfect squares. So this is somewhere between 8 and 9. And I can see that this is 9 away from 63, and it is only 8 away from 81. So it's pretty close to right there in the middle, but it's a little bit closer to 9 than it is to 8. So it's probably like 8.55 or 8.6. Let's go ahead and let's just pull up the calculator here and see what it is. 73 square root. Look at that, 8.54. I had a pretty good guess when I said 8.55, right? All right, so now we're going to go ahead and use the calculator to approximate the radical cube root of 103. You're going to have to use a scientific calculator for this, a basic. I don't think that this is going to be able to give me any exponent that I want. No, it won't. So I'm going to have to change calculators here. That's okay. That's why I have this calculator on here. So I like my TI-84 Plus for this, but you may only be able to use a TI-30, something like that. So we're going to go ahead and I'm going to do it like you would have to do it on a TI-30, where you would use the exponent. It's not going to pop up like this. It's just going to put a caret. And you're going to have to put in your, I'm going to turn off math print on this so it looks more like what you would get with a TI-30. So let me turn math print off. There we go. 103 raised to the, and then you have to put in parentheses your exponent of 1/3 power. Not every calculator has a cube root button. This calculator does have a cube root feature, and I'll show you that in just a second. 4.6, it says to round to 3 decimal places. 6, 8, 5, 8. 6, 8, 8, because 7, 5 is going to round up to 8. Okay, so if I put in, this one puts things in first. This is if I want a root that's not a cube root. We might get one of those in the second where I want an xth root. But cube root of 103 is going to give me the same answer as raising it to the 1/3 power. I'm going to go back and turn my math print on now because it's easier for me to write things in here that way. Okay. That was number 6. On to number 7. Use the properties of exponents to simplify. A to the 7/8 divided by A to the 3/8 is A to the 7/8 minus 3/8 is A to the 4/8, which is the same thing as A to the 1/2. 4 goes into 8 2 times. So that's the same thing as the square root of A. Number 8 asks us to raise x to the 4/3, y to the 3/5 to the power of 15. And when we do that, this is going to be x to the 4/3 times 15, y to the 3/5 times 15. 3 goes into 15 5 times. 4 times 5 is going to give me 20. 5 goes into 15 3 times. 3 times 3 is going to give me 9. Scrolling on down here so I can see number 9. Simplify, assume that all variables represent any real number, positive or negative. So 7 root 45. We're going to break that up, that square root, into the part that's a perfect square and the part that's not a perfect square. This is going to be 7 times 3 times the square root of 5 is going to be 21 root 5. I have a rule that I might have mentioned one point earlier in the videos when we talked about absolute values, that said it was going to come back that when we have the square root of x squared and we're not sure whether x is a positive value or a negative value, we're going to have to put absolute value bars around it. So that's going to come up in this next problem here because it says that x can be any value positive or negative. So we've got the square root of 16x squared is going to be the square root of 16 times the square root of x squared is going to give me 4 times the absolute value of x. I cannot assume that x is a positive number here and not put the absolute value bars around it. Number 11 asked me to find the fifth root of negative m to the 18th, p to the 20th. All right, it's an odd root, so I'm allowed to have the negative sign here, but I'm going to look at the fifth root of the negative 1 that's sitting there, and the fifth root of m to the 18th, and the fifth root of p to the 20th. So what I'm going to do is first, fifth root of negative 1 is negative 1. I'm just going to write down the negative sign. Now I'm going to do remainder division. I'm going to say 5 goes into 18 3 whole times with 3 left over. So I'm going to get m to the third. I'm going to have a fifth root left over here with 3 m's left on the inside of it. Now 20 divided by 5 goes in evenly 4 times. So I'm going to have p to the 4th on the outside there. And that's it. So I don't have to worry about absolute value bars when the index here was odd. I only have to worry about it when there was a even power on the inside, an even root here, and the exponent when it comes outside is an odd exponent. So because this went from even on the inside to odd on the outside of an even root, that's where I need absolute value bars. Now we're going to simplify the cube root of 56x to the 5th. 56 is not one that I'd expect you to be able to do the cube root off the top of your head. We're going to use a factor tree for it. 2 times 28, 2 times 14, 2 times 7. So we see that there's a group of 3 2's that are going to come out. And we've got 7 on the inside. Then there's a group of 3 x's that come out, and I'm left with 2 x's on the inside. Now they want us to simplify the square root of 5 times the square root of 10. This is the square root of 5 times the square root of 5 times the square root of 2. So these two like square roots multiply together to make each other go away, and that gives me 5 square root of 2. When I have square roots that are being divided like this, I can put them beneath a single square root sign and simplify the fraction, and it gives me the same answer. Only factors are 22 or 2 and 11, so I don't need to simplify that anymore. Remember, when you do this though, we don't leave a fraction inside of a square root, and we don't leave a square root in the denominator of a fraction. In both cases, we're going to have to rationalize the root. So when I get 17 over 64, this one's fine because I'm going to leave the 17 up there. The 64 is a perfect square, so we're not going to have any square root left in the denominator here. Which of the following are like radicals? That means that they're going to have the same thing on the inside once I simplify them, and they would be like terms that I could add. So 9 comes let's see, 72 is 9 times 8, which is 4 times 2. So this is 2 times 3 is 6. Root 2 is that one. This one's 5 root 2. This one is 2 root 7. This one is 5 root 2. And that one is 2 root 3. So the ones that are the same, that are alike, are, it doesn't say they're equivalent, it says they're like radicals, which means that they can be added together. So root 72, 5 root 2, and root 50 are the ones that are like radicals. Circle the answers there. So that's it. Now we're going to have to simplify and see which parts are alike and add or subtract my like terms. So this is going to be 4 times 5 is 20. Square root of 4 is 2. 2 times 4 is 8. Leaves the 5 on the inside. This is just a perfect square. And 9 times 10, 9 times 20, excuse me, and 20 is going to give me another 4 comes out as a 2, 3 times 2 is 6. So now I'm going to have 8 root 5 minus 6 root 5 plus 7, give me 2 root 5 plus 7, and I usually write roots last, so 7 plus 2 root 5. Now we're going to perform the indicated operation. Notice the cube root here is over the entire fraction. So this is the cube root of 7x over 12 minus the cube root of 7x over, and the cube root of 27 is 3. So we're going to have to multiply by 4 over 4 to make a common denominator. This is the cube root of 7x minus 4 cube roots of 7x over 12, and give me negative 3 cube roots of 7x over 12, and 3 goes into 12 4 times, which is negative cube root of 7x over 4. Perform the indicated operation, simplify if possible. So when I take root 3 times root 3, that's 3. When I multiply the insides of these roots, I get 18. 18 has a perfect square of 9 as a factor. It simplifies like that. Now, what happens when I have binomial like this and a binomial like that? We're going to FOIL again. Hopefully, we end up with like radicals in the middle that we can add together. And hopefully, we end up with whole numbers for the first and the last. So we get 4 minus 8 root 7 minus root 7 plus, remember, a negative times a negative is a positive, 2 times 7. 2 times 7 is going to give me 14, so 4 plus 14 plus negative 8 root 7 minus root 7. That's a 1 root 7. Don't forget that there's an invisible 1 there. So this is going to be 18 minus 9 root 7. Now we want to rationalize the denominator. To do that, we're going to have to multiply by something top and bottom to make them a perfect square, to get rid of the square root sign here. we're going to assume in this case, even though it doesn't tell us this, we're going to, let's not assume. Let's say we're going to multiply by 2x and 2x, okay? We don't know whether x is positive or negative, so we're not going to assume anything. I would like to assume that x is a positive number, but I can't do that here. So this is going to be 4, and then the square root of x squared is going to give you the absolute value of x down here. And then this is going to give me negative 14 square root of 2x. And I'm going to take out my common factor of 2 when I do that. And this is going to give me negative 7 root 2x over 2 absolute value of x. I had to use my absolute value sign there because I put an x squared inside of a square root sign to get rid of the square root sign, and the square root of x squared might give me a is going to need to be written as an absolute value bar in case x was a negative number. Okay. Let's go ahead and rationalize the denominator here, where it's just numerical. This should be easier. So I need to now get 3, total of 3 2's, right? 2 squared is going to be 4, but this can give me a 2 in the denominator down here. 10 cube root of 4 is going to give me 5 cube roots of 4. Now I want to rationalize, and this is more like what you're going to see in pre-calculus. We're going to have to multiply by the conjugate pair. And so when I see in the denominator that I have 3 minus root 6, I'm going to multiply by the conjugate pair of 3 plus root 6. This goes back to that rule about a plus b times a minus b is always going to give me a squared minus b squared. So one of the ways to make sure that I'm not going to end up with a middle term, actually this is the only way to make sure I'm not going to end up with a middle term and that I'm going to get rid of any square root signs, because the perfect square is going to square the part that has the square root and get rid of it. So my denominator here now is going to be 3 squared minus the square root of 6 squared. And in my numerator, I have 1 plus root 6 times 3 plus root 6. We'll simplify that in a second. It's going to be 9 minus 6. This is going to be 3 plus root 6 plus 3 root 6 plus 6. 3 plus 6 is going to give me 9. And I have 3 plus 1 is 4. My denominator down here is going to be 3. And so I might, in some cases, want to simplify this to be 3 plus 4/3 root 6. If I need to see the part that is rational separate from the part that's irrational, I might want to do that. So definitely going to want to do that when I get to the part where we have imaginary numbers, and I want the real part to be separated from the imaginary part. All right, let's go ahead and solve this. And we're going to solve it by subtracting 4 from both sides to isolate my root. Remember, I warned you that some of these you're going to get extraneous solutions to them, and you're going to need to check your answers. Now, to get rid of the cube root, we're going to cube both sides. So that leaves me with x minus 7 is equal to -4 times -4 times -4 is going to give me a -64. I add 7, and this is going to give me x as a -57. Go ahead and check your answer. 4 plus the cube root of -57 minus 7 Is that equal to 0? 4 plus the cube root of negative 64. 4 minus 4. Yes, 0 is equal to 0. We're in good shape there. Square root of 3x minus 2 is equal to x minus 4. So remember that 3x minus 2 needs to be greater than or equal to 0. 3x needs to be greater than or equal to 2. X needs to be greater than or equal to 2/3 for any acceptable answer that's not going to violate the domain of my original. Let's make sure that that happens here when we square both sides to get rid of the square root, because we've already isolated the root. 3x minus 2 is equal to x squared minus 8x plus 16. I don't know if you notice it, but by me getting rid of the square root sign, I changed the domain. That's why I need to know this original domain up here before I get started with this problem. All right, let's take all the terms over to the right-hand side. When I do that, it'll look like this. Both negative. 2 and 9. X equals 2, x equals 9. Let's go back and check my answers. Make sure that they work. Is 2 minus 4 can give me an answer that I can get from a square root? It's not, because I can't get a negative answer from a square root, right? Not from a positive square root. If I look at this, this would be 6 minus 2 is 4. Is that the same thing as 2 minus 4? Is 2 the same thing as negative 2? It is not. So this is what we call an extraneous solution. Let's look at 9. 27 minus 2 is 25. Is that the same as 9 minus 4? 5 is equal to 5. So that's a good solution. Sometimes you get 2 answers, sometimes you get 1 answer, sometimes you get no answers. You just need to check out what's going on here. We already talked about number 26. We said that the mathematical symbol for the square root of -1 is going to be the imaginary number I. So now they want us to look and see which of the following numbers here represent imaginary numbers. The first one would, it would be 3i. The second one would, it would be 7i. The third one, no. That's got a negative on the outside, so negative square root of 5 is not imaginary. The square root of -3 is going to be I root 3, so that certainly is imaginary. Square root of 4, not imaginary, that's just a +2. Cube root of -64, that's a -4, that's not imaginary. I root 2, that's going to be an imaginary number because it's got an I in it. The ones here that are imaginary are root -9, 7i, -3 to the 1/2, and I root 2. Those are your imaginary ones. Now they want us to simplify using the imaginary unit. So this is going to be root -1 times 9 times 8, and 8 is 4 times 2. So this is going to be 3 times 2 is 6. I root 2. Now 5 root -2 is going to be 5 times root -1 times root 2. It's going to be 5i root 2. Root -288 is root -1 times root 144 times root 2. So this is 12i root 2. Root negative 50 is root negative 1. 2 and 25 is 5i root 2. Root negative 12, negative 1, 4, and 3 is 2i root 3. Now they want us to write something with the imaginary unit that looks like it might eventually be the answer from the quadratic formula. You may or may not know the quadratic formula at this point. I'm going to write this as this. All right, that's a 2. 2 goes into there 3 times. Now we have 16 is 4i root 2, like that. 2 goes into 4 2 times. It's negative 3 plus or minus 2i root 2. Wire is needed to support a vertical pole. It's 18 feet high. I have the guy wire attached 8 feet from the base. Okay. Approximate the answer of the length of the cable needed to 3 decimal places. We're going to have to use the Pythagorean theorem. The a squared plus b squared is equal to c squared. So c is going to be equal to the square root of a squared plus b squared. So we're going to say the square root of 18 squared plus 8 squared, the square root of, let's not even bother with the square root because it tells us to approximate it with our calculator. Let's go ahead and say the square root of 18 squared plus 8 squared. You might need to, if you have a simpler calculator, you might need to find 18 squared and 8 squared first before you find the square root. It says 3 decimal places, so 19.698 is approximately. Make sure you use your squiggly equal to signs. I didn't draw very well there, but make sure it says approximately equal to. And these are in feet. Let's go back and let's show you how to do this with a more basic calculator in case that's what you have, that we're going to have to find 18 squared plus 8 squared is equal to 388. So we need the square root of 388. And take the square root of that, and that's where we get 19.698, right? Okay. Now we're going to find the missing side of this triangle. Where this side is 4, this side is 10, this side is x. Again, we're going to be using the Pythagorean theorem here. X squared plus 4 squared is equal to 10 squared. X squared plus 16 is equal to 100. So x squared is going to be equal to 84. That's not a perfect square. Now remember that x can't be a negative distance. It's going to only have to be the positive answer here, called the principal square root, because distances are not allowed to be negative. So x is going to be equal to, the first thing that I see that comes out is 4 times 21. X is equal to 2 square roots of 21. That's my exact answer. And that's what it asked for. It asked for an exact answer as a simplified radical. So now the last question here asks us to find the distance between the points 9, 4 and negative 9, 10. So 9, 4 is somewhere over here. Negative 9, 10 is somewhere over here. Want this distance here. We're going to use a right triangle here to say that this distance from negative 9 to 9 is 18. And this distance from 10 to 4 is 6. So we're going to say that the distance d is the square root of 6 squared plus 18 squared. And the formula for that, just if you didn't catch it, was the distance is equal to the difference between the x values squared plus the difference between the y values squared. Addition doesn't matter. I did y values before x values, but the distance here is the length of this side. It's not going to matter whether subtraction comes out to be positive or negative because I'm going for the square of the distance. So we are having 18.974 as our answer. Oh, it says give an exact answer, excuse me. So we come back here and say that I want what 6 squared plus 18 squared is without the square root. So 6 squared plus 18 squared is going to give me 360. So the biggest perfect square that I see there is 36, leaving me with 10 on the inside. Is 6 square root of 10 is my exact answer. So no approximation here. This is an exactly equal to. And that's our last problem for MTE 8. I am going to write up here for you something that can be done in MTE 8, though we're going to do it more in MTE 9, which is that if I have the equation ax squared plus bx plus c equals 0, the solution or solutions to this problem come in the form of x equals negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. So you may be asked to simplify these radicals for this, figure out whether the answers are going to be real or imaginary or complex or whatever for part of this for your MTE 8. It's definitely part of MTE 9, though, where we deal with quadratic equations. This is a quadratic equation up here, and we want to graph them and find solutions to them. We're also going to be doing something called completing the square down here. Much of what we talk about in MTE 9 next time is also going to be covered in the new course, MDE 61, for the VCCS, which is what all this is from, the Virginia Community College System, which is a class that you would take along with pre-calculus to support you in it if you needed to have a refresher on how to do some of these algebra things. So we'll talk about those skills next time, a lot about functions, completing the square, finding the vertex of a parabola, graphing parabolas, and using the quadratic formula. All right, see you in the next video.